Hello, I'm Jake. I'm going to be taking you through thermodynamics question 18.8 in a stepwise manner to show you how to find the equilibrium constant K and the change in free energy when given a reaction. For this question, it says, given the temperature data in the appendix of the textbook, calculate the equilibrium constant and free energy change for the following reaction. HBr plus Cl2 results in HCl plus Br2. The first step is to understand what we're looking for. The question states that we need to find the equilibrium constant K and the free energy change delta. The second step is to balance the equation. In order to do this, you must multiply the HBr by 2 and the HCl on the product side by 2, and then the equation is balanced. The next step is to know the equations that we're going to need to use and the givens from the question. So we are asked to find the equilibrium constant K, which can be found using the Van 't Hoff equation. And the Van 't Hoff equation uses delta H and delta S, which represent the change in enthalpy and the change in entropy respectively. So to find that, we need to use the values pulled from the appendix of the textbook and use the products minus reactants multiplied by their stoichiometric coefficients equation to find each value for each species in the reaction. To calculate the free energy change, or delta G, we use delta G is equal to negative R times T times ln K. We know that T, temperature, is equal to 298 K because we're assuming that this reaction is happening at standard temperature and pressure. And we know that R is the standard, and we know R is the ideal gas constant, which is 8.314 joules per mole times K. The next step is to find delta H and delta S. I created a table here of all the values for delta H and delta S from the appendix of the textbook for each species in the reaction. Here is the products minus reactants equation for delta H. Here is the raw equation without any values plugged in. 2 times HCl plus Br minus 2 times HBr plus Cl2. I put the kilojoules per mole on the outside of the brackets to make the units easier. Plugging in the values, here's what you get. And once you put it into your calculator, you get delta H is equal to negative 81.1 kilojoules per mole. Here's the raw equation without any values plugged in for, right here. And then here is the equation with the values plugged in for delta S from the appendix of the textbook. Once again, we put joules per mole times K on the outside of the brackets to make the labeling easier. And once you put this all into your calculator, you get delta S is equal to negative 1.20 joules per mole times K. The next step is to calculate the equilibrium constant K, which is done by using the Van 't Hoff equation. We calculated delta H and delta S, so now we just need to plug in everything into the equation. Off to the side over here, I converted delta H from kilojoules into joules to make canceling the units out easier. When you plug all the values in order to get rid of the natural log, you must e to the x everything. Once you e to the x everything, you get the value for the equilibrium constant, which is K is equal to 1.42 times 10 to the 14, and it is a unitless value. We can now move on to calculating the free energy change. We use the equation delta G is equal to negative RT times the ln of the equilibrium constant. For your convenience, I rewrote all the givens that we know. The ideal gas constant, which is 8.31 joules per mole times K, the temperature, which is 298 Kelvin, and the equilibrium constant, 1.42 times 10 to the 14. We then plug everything into the equation for delta G. Before I move on to the next step, delta G is going to be in kilojoules. And once you put everything into your calculator, you're going to notice that we have a value that's in joules. In order to turn this value into kilojoules, we do a quick dimensional analysis by dividing the delta G value in joules by 1,000 joules to get negative 80.7 kilojoules. And negative 80.7 kilojoules is our free energy change, or delta G number. Now that we've reached the end of the problem, let's do a quick summary. We found the values for delta H and delta S, which are both necessary for the Van 't Hoff equation. We found this using products minus reactants, multiplying by the stoichiometric coefficients. We then found the equilibrium constant using the Van 't Hoff equation. We then found the free energy change, delta G, for this reaction. And we found the equilibrium constant to be 1.42 times 10 to the 14, and the free energy change to be delta G is equal to negative 80.7 kilojoules. You now know how to find the equilibrium constant K and the free energy change when given a reaction.